Hi friends, today we're going to talk about Chapter 3 of Design Data Intensive Application. In this chapter, we'll talk about the different storage index and different database. Concretely, we will first talk about the LSM trees and B trees of how they construct index, and then we'll talk about the difference between oltp and olap. After that, we'll focus a little bit on the column-oriented storage. Let's get started. So why do we need an index? Imagine this very naive case where you have that method and get method. Set method basically writes your key and value, the first position and second position of the command into the database. Let's say it's a file. And then get function, what it does that given the key provided in the first argument, you scan the document of the database and then you get the values. So what's the problem of this approach? What's the problem with the world's simplest database? The problem is when you have a gigantic database, the lookup time will be extremely long. Whenever you fetch the value, you are scanning over all the rows in the database, so your lookup time grows linearly with the database size. The issue is the ON lookup time. That is why you want an index to reduce the lookup time. The simplest index is the hash index. Hash index has two main components. One is an in-memory hash map, the other is a log structure file on disk. So one is in memory, the other is on disk. So for the hash map, you store key and the location of the values marked by the byte offset. So for example, here, this row, this record is key by 1, 2, 3, 4, 5, 6, and the location of the record is stored on the offset 0 of the log structured file on disk. So this way, immediately the lookup time turns 01 compared to 0. Here comes another problem. What if your log file becomes too big to be held in a single disk? There you go, you have different segments. You can control the file size. Instead of maintaining only one log file on disk, you can maintain multiple segment files. Each one is smaller, and make sure they fit in the disk. At reading time, you first get the location of the values, and then you get the value, the actual value from the log file on disk. And similarly, at writing time, you either update a value by writing it to the disk, or you can add in new values in the log structure file. So there comes another problem. Because you keep appending records to the log file, it gets larger and larger. Eventually, you have to handle the case where the log grows too large to be fit into the disk. That's why we have data file segments. So instead of maintaining one single file, you maintain multiple log files. We call them segments. Each segment has their own in-memory hash map, and these segments are sorted by time. Whenever you look up a value, you look it up from those segments, sort reversely. So you look up first from the most recent segments and the next recent segments. As you can see, you keep appending, then the files will grow larger and larger. What you can do is also that you run the merge and compaction process in the background. What it does is that for two segments, you only keep the key value pairs that are the most recent. You discard any outdated ones. This is called compaction. As you can see right now, hash index turns the lookup time from ON to O1. It also segments the log files and uses merge and compaction in the background to maintain the log files. But why isn't hash index prevalent? There are two major reasons. First of all, as we have just saw, the keys of the hash map must fit into memory. There are cases when you have too many keys and your machine doesn't hold. So that's a restriction. The other reason is because of range queries. Because this hash index, isn't sorted. So range queries will require a lot of random access. It's not efficient. So how do you solve the two problems? That's why we have SS tables, sorted string tables. The basic idea of SS tables is that within each segment, you want to keep all the keys sorted. One apparent benefit of having sorted key is that now your range queries is easier because the keys are sorted. The other benefits is also that the merge process and compaction process is much easier because now you have the keys sorted. You can do more merge sort more efficiently. The other thing when you think about it is that at lookup time, if you don't have access tables, you have to have all the keys fit into memory. But now with access tables, you only need to keep certain keys. And because keys are sorted, you can find the keys with only sparse index, only a certain number of keys, and you don't have to store all the keys in memory. Now let's talk about how access tables are implemented. So let's start with write process. In order to create a new key value pair or update a new key value pair, you first write your records into a mem table. This mem table is usually a tree structure, a sorted tree structure, like red, black tree. And then when this memory table got too big, after a certain threshold, you flash this table in memory to access table in disk. And similarly hash indexes, you run merge and compaction in the background. And at the read time, you first search for the key in mem table, and then if mem table doesn't have the key, you go look for the key in the access table. However, LSM3 and access tables are not the most prevalent implementation for databases. The most prevalent one is B-tree. Here's how B-tree works. So this is a read process. Imagine you are looking for user ID 255. This is indexed into a tree structure. So you can think about this as a root node, and it branch out and branch out eventually to the bottom node. This bottom key, it stores either the value or the location of the value. So as you can see here, this example is saying that this database has about 500 keys, and each tree, it branches out. And at the first layer, it stores the reference instead of the values. For example, here, this reference, it will go to a node that has all the keys that are less than 100. And this reference stores keys from 100 to 200. It will branch out all the way to the child node. This is how B-tree reads. But how does B-tree write? So if you want to write to B-tree, you also need to go from the root node. In this case, you want to add the key 334. You look up from the root node and found the reference that contains the range of your key. You go all the way to here and you found that you want to insert the key. Because this child page has no spare space, this adding new key will actually split this child page into two separate ones. So it will delete this current page and create new two page. So what's the major difference between B-tree and LSM tree? We'll talk about it from three perspectives: write, read, and maintenance. So when B-tree writes, it does in-place overwrite. So it will go all the way to the bottom child page and replace that block. Whereas LSM trees, you first write to the mem table and then flush into the SSD table. And for read, the B tree, you basically just traverse. You go DFS until you get the bottom page. The whole time, the time complexity is O log n. But for LSM tree, first you search in the mem table, that's a tree structure, and then you go to the SSD table until you find the value. So depending on how many level you search, each search, the time complexity is O log n. And in terms of maintenance, unique trait about B-tree. The unique trait about B-tree is that the blocks, the segment is fixed size. Every time you go to the bottom child page, you just overwrite the whole page. It's usually around 4 kilobytes. For the LSM trees, the segment size can be different and requires background, merge, and compaction. So as you can see, the LSM tree write is actually easier because it's more like append first and then merge and compaction. It's an add-on process. Whereas for B tree, you have to overwrite. That's why you need to pay more attention to the concurrency and the locks. So for general rule of thumb is LSM tree writes faster, whereas B tree reads faster. So both LSM trees and B trees, they can be used to handle oltp. So oltp means transaction processing system, whereas olap means analytical systems. So transaction processing system, you mostly use it for online fashion, meaning that it's customer facing. If it goes down, it will be an important step. Whereas for analytical systems, the users are mostly internal analysts. If it fails, it might be not as important step as an oltp, but that's just for the most cases. In general, oltp requires low latency read and writes, and olap needs to handle bulk import. It also has much larger data compared to the oltp. So that makes their accessing patterns very different. In a generic application, you have both oltp and olap. So your oltp online processing, your oltp transactional processing system, it will process the data from customers. And then your olap, it will collect the data as logs and do some ETL so that you can make business decisions, such as machine learning models are usually using those data. And then you can use this data to continue serving the customer. To handle the large quantity of data of data warehouse, people use column-oriented storage. So column-oriented storage basically means that you store each column individually. Why column-oriented storage? Well, first of all, it is really good for compression. Here's an example. The observation is usually that for a column that could have millions of rows, the distinct values of that column is usually much less than millions. In this case, a classical example is a product SDKs. You only have like a few number of distinct value for your product, but you have millions of rows. Here, the book introduced a simple column compression using bitmap. So this is your column values, and for each product, you create a map. So for example, here, this is a bitmap for product 29. If you have 10K values, 10K values in your column, you have 10K for your bitmap for this product. And if this row has this product, it will be 1. And similarly for 30, it's the same. So this is 30, this is 30. Just by using bitmap, it doesn't seem like we are able to compress the space. The actual compression also includes the encoding. So this bitmap can be stored as 9.1. This bitmap can be stored as 10.2, 10 zeros, 2 ones, and the rest are zeros. So the storage of those bitmaps, they are very sparse. The storage can be very space efficient. So as we just talked about, one benefit of column-oriented storage is that you can leverage many compression algorithms. And secondly, we want to talk about the column-oriented storage is a sort order. Similarly as row-oriented storage, you have to have keys and make index. You can choose a primary key where you sort and secondary key where you sort. And you need to build index for the keys. So regarding the index, let's talk about how to write in the column-oriented storage. You have two options. You can use either B-tree or you can use LSM tree. B-tree is in-place overwrite, where LSM tree is append logs. Writing in B-tree is actually much more complex than writing in LSM trees because we are using column compression, and B-tree does in-place overwrite and overwrite pages by pages, block by block. So using B-tree is not the optimal way to write column-oriented storage. That's why they use LSM trees, where you can do append only and write column by column. Next, let's talk about the aggregation. Column-oriented storage is usually used for analytical database, which means that you often have to provide aggregations. That is why they usually have this data cube, where it stores a cache of aggregated results, groups by a certain dimension. So unlike virtual views, data cube is actually a special case of materialized view, where the aggregated results is actually stored in cache and disk. So that's it for chapter 3. We talk about the LSM trees and B trees. There are two different ways to implement index. And we talk about even though LSM tree is not as prevalent as the B trees. But for column-oriented index, you can actually use LSM trees instead of B trees. We also talk about the difference between oltp and olap, the difference between analytical processing system and transactional processing system. So that's it. Thank you for watching. See you next time.